So this is an optimization problem. We want to construct an open box. So it has these 4 vertical sides and the bottom but no top. And the material that we can use is 2400 square inches. And the question is, given this, what dimensions would give us the greatest box by volume? Okay, we're going to have 2 unknowns, the base and the height, and the coordinate will allow us to solve for one in terms of the other. If we call the base x and the vertical sides y, then the surface area is the bottom, which is a square with sides x, and 4 times xy, which is these 4 rectangular sides. Looking at this, it seems that it's much easier to solve for y, so let's do that. So y is 2400 minus x squared, that would be 4xy, so we divide by 4x. We're looking for the maximum volume. The volume of an object like this is base area times height, so the volume is x squared y, and we have an expression in terms of x for y, so we can write the volume as a function of x. It's x squared times 2400 minus x squared divided by 4x. So we distribute, so we have an upside down cubic polynomial, which we know usually looks like this. One of the zeros is at 0. Let's factor it. So this is the function expressing the volume. We can worry about the domain, and probably when we have something with no maximum or minimum, we probably should worry about the domain. X and y should be both positive, and the volume as a function will have a 0 at negative square root of 2400 and 1 at plus square root of 2400. So here the volume is negative. Clearly what happens that if x is greater than square root of 2400, then y is negative. So our domain is just the open interval between 0 and square root of 2400. So what that means is that we're expecting first a relative minimum, which is not going to be part of the domain, and then a relative maximum, which is also an absolute maximum given the domain. So let's see. So the volume as a function of x was minus x cubed over 4 plus 600x. We differentiate that. Now this is an upside down parabola. We know what those look like. Given that this is the derivative, this 0 of the derivative indicates a minimum, and this is the maximum we're looking for, given the domain, right? Where the derivative changes sign from positive to negative. That means the original function changes behavior from increasing to decreasing. Now that's a maximum. So we just have to solve for the 0. So the minimum that's outside of our domain is at negative square root of 800. And the maximum that we're looking for is at x equals square root of 800, which is 10 times square root of 8, which is 20 times square root of 2. Now that we figured out x, we basically know everything because we have an expression for y and the volume in terms of x. So let's read the question, what they want. Oh, this is a nice problem because it asks for the length of the base. So this is our final answer. We're done with the problem. Thank you for watching.